So my goal is to provide you an overview of the last of the chi-square chapter that we weren't able to cover in the synchronic sessions. So this is looking at testing for an interaction effect. Right? So if you'll remember at the end of our last recorded session, and you can always go back and review that session again at any time, we were talking about the idea that if there are multiple levels of an independent variable, there's always the chance that they'll interact with each other, right? And if we're looking at an interaction, we have to test for the interaction before we can look at the effect of the additional variables. So the example that we had looked at was the effect of alcohol and caffeine. Caffeine is likely to speed up reaction time, while alcohol is likely to slow down reaction time. However, what occurs if we give somebody both alcohol and caffeine? How will those interact with each other? That is what we mean when we're talking about interaction. There's an effect of alcohol, there's an effect of caffeine, but we're not sure what happens when we mix them together. All right, so in this case, we're looking at an example where there is no interaction effect, where the effect of caffeine is to reduce reaction time, to speed up our reaction by 25 milliseconds, regardless of any other conditions. Whether we have no alcohol or alcohol present, whether it's 200 milligrams or 400 milligrams of caffeine, there's always the same effect. The same with alcohol. Alcohol slows us down by 50 milliseconds, regardless of the level of caffeine we've taken. Right? So in this case, consuming alcohol or not consuming alcohol does not have an effect on the amount of the reaction time that caffeine alters. Whereas we can also say that consuming caffeine does not alter the effect on reaction time that alcohol has. Right? They are independent of each other. There is no interaction, and we can talk about the main effect of alcohol or caffeine. The other possibility is the presence of an interaction. This is when the effect of alcohol or caffeine depends on the presence of the other. So if there is no caffeine present, alcohol reduces reaction time by 80 milliseconds. However, if caffeine is present, and depending on the amount of caffeine that's present, we see a difference in the reduction of reaction time. Same thing here with caffeine, where the plus 10 milliseconds in the no alcohol condition and the 40 milliseconds in the alcohol condition means the effect of caffeine depends on the presence of alcohol. So where there is a dependency, there is an interaction. So anytime we have multiple independent variables, we need to test for that interaction effect before we can start talking about the effects of alcohol or caffeine, because we get that dependency. So if we look at a table from 13.4, this is looking at the gender and age of characters on a cereal box, right? So the gender is one variable, age is another. And the question is there an interaction, right? If we look at this, we can see that just by sort of eyeballing it, it appears as if there's not a big difference between male versus female gender on children appearing on cereal boxes. However, when we look at adults, there does seem to be a bigger difference. So if we ask, is there a difference in gender on the cereal boxes, you might respond with, well, it depends on whether or not we're talking about children or adult, right? That depends is a hint that we are dealing with an interaction. Right? So we have to test for that interaction. We have to see if that interaction is significant before we can start talking about the main effects. And we can use the chi-square to do that by focusing on our observed values minus our expected values, right? And so the observed values stay the same, right? We're dealing with our proportional data here. So this is the data that's observed. It's the expected values we have to figure out, right? Because if you'll remember, right, our chi-square is based on that idea that it's going to be equal to the observed data minus the expected data squared over the expected data. Okay. So when we ask about the interaction, the expected data is what we would expect to appear in each cell if there was no interaction. That's the null hypothesis. The null hypothesis says there is no interaction. right? So we want to know what is the expected data if the null hypothesis was true, that there is no interaction. So we have to calculate when we're looking at these cells, right? So if you imagine we have any data set where we have, two levels of a variable, we are going to have 4 possible cells. Each cell constitutes one of our observed data, right? We have to ask then, what would the expected data be in this cell if there was no interaction? And if there is not an interaction, we would expect the difference between the observed and the expected to be very small, and that's what we're testing. So it turns out that there is an equation that can tell us what the expected data should be in each cell, and it's based on what we call marginal sums. So the idea here is we have rows and we have columns, right? So this is the first row, this is the second row, this is the first column, this is the second column, and then we have the total number of observations, right? So remember, the total number of observations is not adding together both the column and the rows, right? That would double it up. But what it's about is adding up just the total number of observations. So you could just add up the total number of row or the total number of column. And there is a specific equation that we can use called the expected frequencies equation, which is the row total multiplied by the column total divided by the total number of observations. Okay? So each cell is going to have a different combination of row and column. Right? So if we look back at the child data here, right, we can see that this cell here is going to have a specific row value, 58, column value, 153, and then the totals don't change. So our expected is going to be equal to our row, 58, times our column of 153 divided by our total of 222. And if you do the math, you'll see it comes out to be about 40. However, if we go to the adult male, it changes, right? Our new row is 164, but our column stays the same. So our new equation is going to be the 164 times the 153 divided by the 122, right? So you can calculate the expected for each cell using this equation. Once you've done that, all you have to do is plug them into the standard chi-square equation, right? Observed from each cell minus the expected from each cell squared divided by the expected from each cell, and you sum them up. The degrees of freedom is the number of columns minus 1 times the number of rows minus 1. Look that up in your chi-square chart and accept or reject the null hypothesis, and you're done. So let's take a look at an example of preference for digital, analog, or undecided in selecting watches for people under 30 or over 30. All right, so pause the video here and attempt to calculate the observed and expected values and do the chi-square. All right, so pause here, work out the problem, and then come back and we'll do the answer. Okay, so hopefully you've had a chance to work through the problem. So the first step is to determine what our row sums are, right? And what our column sums are, right? So we need to add up each of these. So if we do that, what you'll find is that we get, for the first row, 90 plus 40 plus 10 gets us 140. 10 plus 40 plus 10 gets us 60. And then each row, 90 plus 10 is 100, 40 and 40 is 80, right? And 10 and 10 is 20. Our total number of observations is 200, right? Remember, some students take the 200 from the column and the 200 from the rows and try to add them together to 400. No. Just keep it to the 200, all right? Once you've done that, we have to compute our expected frequencies, right? Remember, it's column times row divided by total. So if we go through here and we do the math for each combination of column, row, and total, this is what you'll find. So these are the expected frequencies for each one of our cells. All right, so now sometimes I like to lay this out in the table so we can see it all together. All right, we have our observed frequencies. All right, the observed frequencies were what were given to us in the cells. Right, the expected frequencies is what we just calculated. The observed minus expected. Square those values, then divide by the expected again, and that's going to be the individual chi-square for each cell. And then all we do is we take each individual chi-square for each cell, we add them all together, right, and we get our total chi-square of 38. We then compute our degrees of freedom, which is the number of columns minus 1 times the number of rows minus 1. That's going to get us 2. If we use a alpha of 0.05, we'll get a chi-square crit of 5.99. We can see that we can reject the null hypothesis that there is no interaction, and there is an interaction effect. All right? So one thing to keep in mind is if an interaction is present, it often doesn't make sense to talk about the main effects. The main effects are meaningless because the effect of one variable and the other depends on the other, right? So the idea of trying to determine the main effect of each variable doesn't make much sense because the interaction tells us there's a dependency. So oftentimes once you've determined that the interaction is significant, you're done. Trying to calculate main effects is often meaningless and can often lead us astray. So that's how we use the chi-square to test for interaction effects in our proportional data.